Let's do it. So, good afternoon to everyone. In this presentation, my goal is to propose a graphic three-dimensionality to the distortion points within the scope of the sonic domain theory. But before, I would like to start my presentation by briefly talking about the theory itself. As a composer and a music theorist, a question has been guiding my endeavors. The question is how to understand and measure time and space in music, and how does this understanding affect my compositional and analytical processes? Several music theorists and composers already had given some answers to that question. Among them, great theorists and composers such as Jonathan Kramer from Columbia University and the writer of the book Time in Music from 1988, Christopher Hastry from Harvard University and writer of the book Rhythm as a Matter from 1997, Zenax, who wrote the very well-known book Formalized Music, Messiaen, who wrote a true masterpiece, his Traité de rythme, de colère et de dontologie, among several widespread approaches about time. These approaches and almost every approach about time in music are related to the question of how do we perceive time, which is essentially a cognitive issue. However, what has been driving me to this point so far is not mainly how we perceive time, but how can we model time and space in music. For that, I am sure that I'm not discovering a new mathematical foundation about time and space in music. Physics explains and provides mathematical models to describe every sound observable in nature. Every sound produced is already physically well known. In simple words, my work consists of building a theory which I call the sonic domain theory, based on a philosophical approach to time, which allows me to compose and analyze music. I haven't time enough to go deeper on that question, but for me, time in music always emerges from space. That is the definition of emergent time from the physicist Lee Smolin, which I take as a foundational basis for the theory. Once this premise is settled, I can move further on two major assumptions. The musical score is a sort of space that captures time. Events on the musical score can be mathematically described. That being said, the very first concept, is the PEC. PEC means expressive compositive potential. It's about a musical idea in its essential feature, something that can be understood as the most primary musical material. The PEC is constituted by the confluence of three parameters: pitch, time, and dynamics. We use a matrix to describe the PEC as a set of vectors. In the first row, the pitch component is plotted. On the second row, the temporal component. On the third row, the dynamics component. Vertically, the vectors that compose the matrix appear. As you can see, the pitch component is described using pitch classes. However, all registers are considered. In other words, the PEC operates on P space according to Maury's approach. For the temporal component, it was assumed that the quarter note has 1 second of duration, and by this, all notes are proportionally divided. Considering the dynamics component, a table of amplitude division in MIDI language was applied. The figure reveals how a music material can be transcribed on a PEC matrix. The next step is to reveal the concept of perturbation. Perturbation of the space is simply a shifting of patterns. It's well reflected on temporal component. These two contrasting examples, Verban's Opus 11 and on the top, and Bach's Prelude No. 2 from the Well-Tempered Clavier, shows that perturbation can be understood as the similarity or dissimilarity between space variation as a function of time. In other words, is a variation of speed, fast notes against slow notes. The temporal difference between events is indeed the very notion of causality. And that's how space ordering affects time. And that's why time in music emerges from space. On the bottom example, a space minimally perturbed is shown. That's because there is no temporal, pitch, or dynamics variation. In my other paper present at this conference, it was revealed how intravectoral analysis shows perturbation or the lack of it. A two-dimensional graph reveals the perturbations and the exact point where the shifting occurs. Time in seconds is being measured on the x-axis. Events are being plotted on y-axis. The first event is a half note. The second and the third events are both eighth notes. The fourth, the fifth, and sixth events are the triplet. Finally, the seventh and the eighth events are both 16th nodes. I call this graph as linear interaction because it reveals perturbation levels taking one parameter at a time. In this case, the temporal component of the pack. There is another graph called multilinear interaction that shows perturbation levels on two or more parameters simultaneously. Then arises the concept of the index of perturbation, which is precisely the point in time where the shifting occurs. Therefore, a large number of indexes of perturbation indicates a high level of perturbation of the space, and the lack of these indexes indicates a low level of perturbation. Just for information regarding to texture, I've developed a specific mathematical model called the texture function. This model apprehends textural parameters such as compression, decompression, interdependence, dependence, confluence, and divergence. Okay, coming close to the subject of this paper, I will present the concept of density dynamic and the distortion points. Density dynamic, it's a numerical value obtained through mathematical model, and it results from the vertical reading of events relating the pitches and dynamics involved. That is, they are points in time where occurs pitch superpositions as chords and or blocks. I proposed this mathematical model in my thesis. For dn, I mean sonic mass, which is the density number proposed by Berry in 1976. It concerns the amount of components sounding simultaneously. And it's very well known, this concept. For AI, I mean the sonic volume. It is the interval range, the distance in half tones from the lowest note to the highest one. In physics, the ratio between mass and volume quantifies the density of a given body. We start from this relationship to propose the density dynamic. In music, the ratio between density number and the interval range, that is DNN over AI ratio, consists of what Berry conceptualized as density compression. However, in addition to density compression, as proposed by Berry, I listed dynamics as a major factor regarding distortion points. Imagine two musical examples with the same density number and the same interval range being played. The difference between them will be revealed if they are being played with different amplitudes and different timbre. But timbre is not a primary parameter in the scope of the sonic domain theory. Therefore, the DNA over AI ratio reveals part of the information about the temporal quality. When dynamic is added to this ratio, then density dynamics arise. The symbol Omicron I is called intensity coefficient, and comes from a table of amplitude division in mid language. We are now going to list to 6 different chords played on Schoenberg's Op. 11 from piano. Okay, the question is, which chord has a higher level of density dynamic? These are the results. I say that in this passage, there were 6 distortion points, and the third one had the highest level. You can see that the second, the third, and the fourth chords had the same number of components, the same dynamics information, but not the same interval range, and yet the same duration. That's indeed why the third one had the highest level of distortion. Finally, the question that brought me to this paper is how to plot the distortion points in 3-dimensional graph. Well, for sure, there are several forms of doing so. I have just found a way of 3-dimensionality using cones, which is a geometrical figure. Taking distortion points number 1, 2, and 3 from Schoenberg's example, you can see at the bottom a 2-dimensional graph. It represents these 3 distortion points and how long they last. In other words, the duration. On the right side, you can see a simple formulation to allow the shifting from 2 dimensions to 3 dimensions. And I will describe briefly this equation. The center of the base of the cone is the final distortion point minus the initial point distortion point. It's a very simple. The height of the cone is the number revealed by density dynamics, and the radius of the cone is the temporal component divided by 2.
Sorry for interrupting you, but your time is over. Could you conclude in 1 or 2 minutes?
Yeah, I think 30 seconds.
Okay, thank you.
This is not a final resolution to the main question of this article. This is a simple proposal. For that, I conclude that the application of the cone in principle is satisfactory, for it reveals what was already foreseen. That is not the duration of the distortion point that gives them more quality, but the density dynamic. This understanding opens new doors to the present work, because from it, a number of new possibilities can be proposed towards the 3-dimensionality conceptuality formulated by the sonic domain theory. Thank you so much.
Thank you, Andrea. Very interesting your paper, and probably we'll have some questions at the end of the session.
Thank you.
Thank you. I will